All right, good afternoon, and welcome to ECE 164. So today we're going to do the live discussion component of this. Let me first open it up and ask if there's any questions about lecture 1 or lecture 2. Have you guys watched lecture 1 or lecture 2?
Yes.
Right. One yes. By the way, this is meant to be much more interactive. I don't want the discussion section on Wednesdays to just be me talking. I get to record and talk plenty, and then have to go fix my mistakes. So thank you for pointing out that on lecture 2. I went and fixed my boo-boo. So the new lecture has a little tagline that fixes that. All right.
I have a question about the non-disclosure agreement. So once we email the person in charge of that, should we expect an email in return telling us that we've been granted permission?
Usually not. So yeah, that's a great point. Let me put this up just so that everybody gets to see it. Sorry, I have about 50 windows open. All right, so part of the reason that we have to sign this non-disclosure agreement, can you guys still see it? Yeah, okay. Part of the reason why we have to sign this is indeed to protect the intellectual property of the tools that we are using and the files. So you guys need to sign this. You need to upload it to Canvas. That's for me. And the other thing is you need to send it to Miriam. And that was kind of your question is, after you send this to Miriam, a couple of comments that I'll make. One, try to make it as easy as possible for her. I have 100 students in 164. Several hundred people are emailing her with requests for things in adding accounts. So almost always she does not reply back. I will show you in just a minute how you can check to see if your account was granted. But the one thing I will say is that you can help her out. And helping her out usually entails things like in the email subject, telling her it's EE164, telling her your username, telling her your name, just making it very easy that there's no back and forth or kind of clarification that she needs in order to get the ball rolling. Other questions about the NDA? All right. So there are a couple of other things that I wanted to discuss and share.
Dr. Hall, real fast, I think you mentioned this the last lecture, but when we come to this Wednesday, is it generally a 2-lecture thing, like watching them Tuesday, Thursday, or is it just the previous Tuesday, or what kind of material should we have prepped for the Wednesday?
Yeah, I would say minimally, the Monday, Tuesday. It's fine if you also want to go ahead the Thursday, Tuesday. It's fine if you also want to ask questions for what would be tomorrow's lecture. I'm going to post them at the start of the week so that you can watch them at your leisure and whenever you can work it into your schedule. That said, I'm also happy to answer questions. If it's week 10, I'm happy to go back and answer questions on week 1.
Okay, thanks so much.
Oops. All right, so one of the things that we are doing in this class is that we are using a technology that is, it's a real IBM technology. And so that's why we have to sign this NDA, but let me show you a little bit about this technology. And then I also want to show you Cadence for 1 second. All right, so what we're using is it's 180 nanometer CMOS technology. This also happens to be a very versatile technology that can be used for RF communication, so radio frequency communication. And it's a very powerful technology in the sense that it also is a bi-CMOS technology. we're not going to use this aspect of it, and we're also not going to use the RF aspect of it. If you want to get kind of a few high-level overview of this, and I posted this online as well, this shows you just kind of some high-level features of this technology. We won't get too much into a lot of these features, but what you'll see is that it gives you some parameters, but it doesn't tell you everything. I mean, here, if you were designing a circuit, VT is pretty important. Knowing the oxide thickness, knowing the off current relative to the on current. So this has some of the numbers that we need, but as you can see, if you were to think about kind of square law equations as one example, it does not tell us what Kn or Kp would be. And so one of the things that we're going to do on homework 1 is we're going to set up simulations in order to extract that. And I'll show you how to do that in just 1 second. Importantly, it also does show you the maximum voltage that we can apply on this technology. It's 1.8 volts. Do you guys understand where this limitation comes from?
No, where does it come from?
So it turns out that when, technology, as I said, people have been scaling technologies for a long time. And it started off with, 5 micron, 10 micron, very large devices. And originally, the scaling was proceeding with what's known as Dennard scaling. And so in Dennard scaling, you basically tried to keep the electric field constant. And so you scaled all of the dimensions proportionally. You can see what happens, though, very quickly is that the oxide thickness, this is the gate oxide thickness, it becomes very thin. And so, 3.5 nanometers is not all that many atoms. And as they continue to scale the technologies and beyond this, it became impossible to do this called a constant field scaling. And so they stopped scaling the field. Importantly, as I scale the field, I need to scale the voltages down too. And so the maximum voltage that you can apply to these technologies is really limited by breakdown, i.e. destructive device breakdown. One example of this, if you've ever hooked up the power supply to a chip backwards, you can see the magic smoke, as we'll call it, come out of the chip. It's really that you cause destructive damage to the chip. We've reverse biased things, and we have excessive current that's resulted in local heating that's physically damaged the chip. And so the maximum voltage that we're going to have in this class, VDD, is 1.8 volts for this technology. This is not terrible. As you go to more advanced technologies, this will even go down to where it's settled now at about 1 volt for a lot of very advanced nodes today. All right, so one of the benefits that we do get with this technology here is you can see that there's a lot of different devices. We're not going to focus on many of these. We will typically use just kind of the standard NFET and PFET, but technologies sometimes offer other devices, things like zero VT. So devices where they've implanted the substrate underneath the gate such that they've shifted VT with implants to be 0 volts. Isolation. So this is an example of what's called a deep end well. So very much like we put our PMOS device inside of a well, you can also put an NMOS inside of a well. That's called an isolated NFET or a deep end well NFET. They also have high voltage or high VT devices. They have different gain devices. They have thick oxide devices where now the voltage can go up instead of being limited by this thinner oxide of 3.5 nanometers. These have thicker oxide, 7 nanometer, for these different devices. And so this document in general, I don't want to go over too many of the parameters in here, but it gives you a lot of technical details about this type of technology. And so I would recommend looking through this and then coming back and revisiting this as you play around with the technology a little bit. All right, so now there's 2 very important things that we need to get started on. One of which is getting remote access to cadence. So I've shared with you and posted this in the CAD section, a a couple of documents on using Cadence, but let's start first with the one on accessing Cadence. All right, so what we have here is that all of the software that we're going to use in this class, that is namely Cadence, it's given to you guys and me free. And the vendor is very smart. This software in industry is very expensive. Does anybody want to take a guess of how much this costs per seat at a company?
10,000.
10,000? All right, keep going.
Wait, the price for what exactly?
Price per seat. So, like for example, if you buy a seat or one license of Microsoft Office, for example, that costs $100. What do you think this particular software that we are using to design integrated circuits costs per year per person?
200,000.
So it depends a little bit on the configuration, but it's anywhere from 100,000 to $1 million per seat. And the software vendors are very clever and smart. They give it to universities like us for free. In a sense, they're like drug dealers. They give you the first one to get you sampled and get you hooked, such that when you go to the workforce, you can tell your employer that you know how to use Cadence and that's what tools they should get. These are all hosted on these servers. Okay, so IN6-ECE-XX, where XX is a number between 11 and 18, .ucsd.edu. Importantly, you need to be on the VPN or physically present on campus for this to work. And so the very next slide and a few slides is on setting up the VPN and making sure that all works. If you don't know your account, you can look up your account with this link. It should be ECE 164F, and then this year they added 20 in front of that, followed by some random letters. And so there's just instructions in this document. A tutorial basically walks you through the entire process for both Windows and Mac in order to get connected to the servers. Has anybody had any problems, or has anybody not tried this yet?
I haven't tried it yet. I know I've got the VPN set up, and that seems pretty straightforward. But there's another program I'm trying to get to work on the servers. I think a different server, but on UCSD, and I know that's been giving us problems. I don't know if these ones are a bit more straightforward.
The likely answer is no. So I would encourage you. I'm going to show you homework 1 in just a minute, and homework 1 is going to depend on having access to Cadence. And what I don't really want is for you to be gated by submitting your NDA to Miriam to get access to this. So if you haven't done that, you really need to do that ASAP. I personally cannot do anything. The TAs cannot do anything. Just because we have your NDA, I do not have access, nor do the TAs to allow you to have access to this. We do not have the permissions to do that. And the last thing I'll show you just 1 second, and then I'll talk about the homework. At the end, make sure that you close this. So it's important that you actually sign out of the server and close it down, and don't just leave this running. Because if you leave this running and 40 other people in this class leave it running, along with the other 10 classes using the server, pretty soon all of these servers get pretty slow. And that's not very much fun for anybody. All right. All right, so the next thing I guess that I will show you is homework 1. Do you guys still see it when I move it to this screen? You don't, right? I have to leave it over here. Okay. All right, so homework 1, this is gonna go out. It should be live on Canvas immediately after class. It's due next Wednesday, submitted on Canvas. My preference is probably that you write them out by hand and then either take pictures or scan them in and upload that rather than try to type out equations. It may look easier, but I don't think there's a lot of value in spending your time writing out the equation. All right, so the first problem, we're just going to analyze a pretty straightforward circuit. And you'll see that many of my problems have many parts. This is to kind of prepare you for the exams that are also coming up. We'll start off with kind of a setup and then we'll probe different aspects of this as we go through. So there's a problem on an NMOS cascade where we're putting two amplifiers back to back, and it's asking some kind of general equations that we're going to try to solve for some conditions in order to kind of look at the per stage gain. The third problem is really talking about linearity. So this is something that we don't spend a lot of time on in this class and probably won't talk a whole lot more than this. But oftentimes when we're analyzing circuits and when we're designing them, we linearize them. And this comes out in the small signal model where we essentially look at only the first derivative and we don't consider any other nonlinear effects that happen. What we're going to do here is we're actually going to look at what you would consider the nonlinear effects and how they result in distortion, and calculate how that would put some bounds on the circuit. So you're first going to calculate without distortion, and then we're going to come back in and limit the distortion and do some calculations there. Then I'm going to have, you have a problem on PMOS devices. Essentially here, we are just going to look at some biasing. It's one of the first times that we're going to start to bias with other transistors rather than using passive components like resistors as we've commonly seen in class. All right, and the reason why I'm showing you homework 1 right now is that you need to do the CAD tutorial, and I'll show you the CAD tutorial in just 1 second. But essentially, this is to make sure that if you are not familiar with cadence, that you get some exposure and have a chance to go through the tutorial, walk through all the steps and have access. And then in the last problem, problem 6, you're going to do some characterization of this technology. The idea here is that very much like if you were just starting at a company and they asked you to start to design in technology X, where X could really be anything. One of the things that you would probably need to do is become comfortable with that technology. And being comfortable would be knowing things like, what is the threshold voltage? What is the transconductance parameter? What do the IV curves look like? And so what we're going to do here is you're going to simulate ID versus VGS, ID versus VDS for an NMOS transistor of this size. You're going to then do the same thing for a PMOS, and then we're going to do some calculations on this data. So you're going to, take this family of curves and go back in and try to extrapolate VT and KN. And we give you a few kind of hints here at how you would size these, assuming various different configurations. The nice part about this is that it gets you in the it gets you in kind of the groove of using cadence in order to do some of these simulations with things like parametric sweeps and running lots of simulations. Any questions about homework 1?
Yeah, Professor, I have a question.
Yep.
To finish the homework 1, how many lectures do we need to watch?
Yeah, good question. So I typically try to keep it within that week. So homework 1 is primarily based on lectures 1 and 2. I think it does bleed a little bit into lecture 3.
Okay.
Although, to be honest with you, I'm losing track of all of the lectures because I'm trying to do them ahead of you. So I'm like a week and a half ahead right now. Any other questions about the homework?
For the last question, when trying to extrapolate the KN and looking at the IAD versus VGS curve, should we be looking at a certain region?
Yeah,
Like,
so you're going to sweep the devices and you're going to see, I mean, absolutely. We're sweeping VGS and VDS to put the devices in triode, in saturation, and you're going to annotate on these plots what region of operation it's in.
okay, thank you.
I did forget, if we want to use the raise hand feature such that I can see you guys, I think that would work well. There's also a few questions in chat that I missed. Let me see. Oh, yes. Austin, are you still online, Austin?
Yes, I'm here.
All right. Austin wanted to make an announcement.
Yeah, can I share screen? It's a lot easier if I can just show the website in the first place. Some of you already know me. So the announcement is, well, I am a tutor in the ECE Tutoring Center. Can you see the website?
Yes.
Lovely. So the tutoring center would normally meet on floor 5 of, or we normally work in floor 5 of Jacobs Hall, but this quarter and probably the next one, due to the pandemic, we're doing everything online. And so if you go to ecetutoring.com and you log in with your UCSD information, you can submit what are tickets and that for you to get help with your coursework. And for this quarter, the tutoring center, and more specifically, I will be able to take tickets for ECE 164. And you see the availability of when exactly I am online for tickets. If you go to the schedule tab, it is approximately, for me, it is approximately 20 hours a week spread throughout the week. So if I'm online, you can submit a ticket, whether it's about the lecture or the homework, and I'll help you through it. Are there any questions with respect to that?
Thanks, Austin. You look busy.
Yeah.
Looks like my schedule.
Yeah, it's mostly 35 tickets.
But it starts at 9 a.m. My day starts at about 5:30, so a little late.
Extra 4 hours of sleep isn't nice. All right. Thank you, and I hope to see you guys there.
All right. Thank you. All right. Were there any other questions about homework, lecture?
So how would you like us to turn it in, like Word document or written copy of the written one? I mean, a photocopy of a written document or?
Yeah, again, my preference is that it's handwritten and then either scanned in or pictures of it uploaded to Canvas, not typed in Microsoft Word.
Would it be good as a PDF file?
Yeah, I mean, if you can scan to a PDF, yes, absolutely.
All right, perfect. Thank you.
I guess my point is just that I don't want you guys to sit there and type out equations. It's not very fast. It's not productive for anybody. And it usually ends up looking worse than if you just hand wrote them.
For sure.
Yeah. All right. Any other questions? Okay.
I have a question related to the lecture too.
Yep.
So in subthreshold region, we take the value of n, right? Of depletion cap, it depends on depletion capacitance and oxide capacitance.
Yes.
I don't see why we shouldn't take that value even in the active above threshold region, though it won't be exactly 1.5 or something, but it will still be not equal to 1, right?
All right. Let me put up the slide to make sure that we're on the same page. So we're talking about this slide. Is that fair?
Yes. Yeah.
Okay. So the important thing to remember is that a MOSFET, the typical conduction mechanism, that is when I'm in above threshold, when I'm in linear or I'm in saturation, it's a drift mechanism. And so the carriers move from source to drain via drift predominantly. The fundamental difference in subthreshold is that it's primarily a diffusion mechanism. And so that's why it acts more like a BJT. A BJT is primarily a diffusion device. Now the device physics, as I'm kind of showing here, it's not cut and dry. It's not either diffusion or drift. And that's where, right around VT and once we start to get above, it's really a combination of drift and diffusion. And so that's why in this class, we are going to limit ourselves to about 150 millivolts overdrive, or putting us into what we would call moderate inversion. And in moderate inversion, it's almost entirely drift. We don't see much, if any, diffusion at that point. Is that related to your question?
Yes. So the value of n,
Yeah.
so does it tend to become 1 or does it still stay at 1.1 or something?
Yeah. So your question, and I wish that I had my iPad working. I came into the office to not have the gardener be mowing the lawn right next to your ear. Unfortunately, my iPad does not want to connect here, so I can't draw. I will work on this. The problem is that, if you look at this N is really a capacitive divider. And in the case of being in sub-threshold, I have a capacitance from this oxide, and I have a capacitance here that is typically what you would call the depletion capacitance. Okay.
Yeah.
When I am in inversion, when I've converted this channel and I've turned the device on, I no longer have this bottom capacitance. So N is actually meaningless in that sense, because I've formed a conductive channel right below the surface of the device. And so to say that N changes, I mean, it is true. The CGS term essentially goes away.
Even if we observe inversion, the P substrate is still does still exist right there. So we will still have the depletion region between the channel which is rich in mobile carriers and the substrate which is P. So
However,
we
I have a
still
conductive channel that's sitting right below the surface here that's essentially shielding it. And that's where in sub-threshold, I don't have this channel that shields it. So I get this nice capacitive divider.
Even if, let's say, the channel is just like a wire, which it's like, let's say it's conducting very good.
Yeah.
But even if we have a capacitor connected from that wire to the ground, we still have the capacitance effect there, right? I mean, we have a capacitance from the channel to the ground or the body.
You do, but
The
you're no longer controlling this intermediate voltage right here via the gate. And that's the big difference. The reason why we get a BJT-like action is that I have NPN, where this base, the voltage is really being set indirectly by this capacitive divider that's formed here.
Okay.
And once I put a conductive channel on here, the gate no longer influences this voltage.
Okay, got it. Thanks.
Yep. Other questions?
I have another question, just not a quantitative one. So, generally, when talking about the DIBL effects and all other effects, which we don't consider in the linearized equations,
Yep.
we say that it is applicable for not so small channel lengths. So, what is it? What does that term generally mean in practical sense? So, 180 nanometers can be approximated with a linear one, or I just wanted practically what is that length?
Yeah. Great question. So let me bring it up here where I can explain this. So your question in particular was about DIBL, so drain-induced barrier lowering. Just to kind of quickly remind everybody what DIBL is essentially that when I put a voltage on the drain, I do not expect the threshold voltage to change. Okay. However, very much like when I put a voltage on the body, I can make this channel either harder or easier to invert. And so we would consider DIBL as a second order effect, a non-ideality of this device. Now, your question, I said that this starts to creep in and become a more dominant factor in newer technologies. Where is this cutoff? Is this cutoff at 130 nanometer? Is it at 65 nanometer? Is it at 7? Where's the hard threshold where this starts to matter? It turns out that it is a little bit gradual. We will see some of this in our technology in 180. It will not be as pronounced as in, say, 65 or 45 nanometer, but it certainly will exist here. And so part of what you're going to do on homework 1 is that we are going to try to fit these IV curves to the square law model, i.e. the model that we derived in this lecture, where we essentially calculated this, right? And what you're going to find is that it fits okay, but not great. And this is going to be reflected when you try to calculate VT and you try to calculate this transconductance parameter. It's not going to be perfect. And partly what we are going to see is some of these second order nonlinearities creeping in. So to your point, do I see this in 0.35 as 0.35 micron as much as I see it in 65? Absolutely not. Will you see it in 0.18? Yes, to a small extent. And that's why, in particular, I like using 0.18 micron for this class. We get to kind of get a sense of some of these things, but it doesn't overwhelm the calculations like it does in some of the other technologies.
Okay, thanks. That's great.
Other questions? All right, one other quick announcement regarding office hours. The TAs are going to start their office hours tomorrow, and I will also have my office hours starting on Friday. I don't want the TAs to sit around the entire time if nobody's going to come to office hours. And so what I've told them is that if nobody shows up within the first 20 minutes, then they're free to kind of leave and let go. So if you do have questions or want to get something answered, make sure that you try to come on the earlier side. That's just not to say that if people have a lot of questions, they're going to leave within 20 minutes. They'll stay the full time that we've allocated. Just make sure that you get there early in case nobody else has questions. All right, any other questions regarding the lecture, regarding Cadence, access to Cadence?
Professor.
Yep.
I do have a question. I'm trying to remote into the server, but I can't. So I'm just trying to use the VNC server. So I'm using Linux. So it should be fine. It's just a VNC server,
Yep.
but I can't because it has like some locks for the different displays.
Yeah. All right, so let me show you this. So essentially what your colleague is saying is that he doesn't use Windows, he doesn't use Linux, he doesn't use Mac, he uses Linux. There are many different ways to access the servers. If you are on Linux, typically what you need to do is you actually need to tunnel into the, you need to set up an SSH tunnel onto the servers, the same servers that are described previously, and then it will forward X. So you need, and you also need to SSH-X. But they have security. So there's half a dozen different ways to connect to the servers. I would suggest starting with whatever one you feel the most comfortable with.
Just to clarify, I did run it through the SSH connection that I have, and it opened the actual application on my like local session. So okay. I don't know if that's how it's supposed to be working. It's kind of slow though.
It's kind of slow.
Yeah.
Yeah.
It's actually very slow for me. I do not know if it's my fault or anything else.
All right, let me show you this in 1 second. I'll give you one other piece of advice. So this is the Cadence tutorial that we've put together. It's very detailed. This is generic to a lot of the ECE courses here at UCSD. So, me and several of the other faculty over the years have tried to keep this up to date. You will notice that there's a few things that are going to be slightly differently, i.e., some of the names, you need to replace these with your account, not the account that's shown here. The other thing to remember is that given that this is meant for not just our class, but for all of the classes, some of the things won't apply for 164. For example, we will not do noise. So you can skip chapter 4. You don't have to worry about this. Some of the other things here, like they're doing Monte Carlo analysis and mismatch variation, we won't do this until later on in the course. And so if you want to skip this for right now, feel free. I don't want to make this too overwhelming, but there are a lot of really neat things that you can do in here in order to really get things kind of dialed in for Cadence. And then at the end, most importantly, where I want to get, there's an FAQ. And this FAQ is, if you are having problems, these are kind of steps that you can take to work through lots of things that we get asked often. The reason why I come here is that I get this one often, that the server is really slow. What can you do? So I'm going to show you how to use this in just 1 second. All right. All right, does this work? Do you guys see my remote desktop?
Yes.
We do see it.
Yes.
Perfect. All right, so I have connected to one of the Cadence servers. And so the first thing that I'm going to do is go to System Tools and open up a terminal. All right, and so it's going to pop up with all of this, and it's going to tell you and remind you that legally you cannot copy anything, that you've signed the NDA. There's a couple of things that I want to show you here. One of which is before you launch Cadence, I would typically run a command called top. And top, if you're not familiar with it, it's the equivalent of like Activity Monitor for a Mac, or what is it in Windows? Task Manager in Windows. It shows you all of the things that are running, but most importantly, up here in this top is what's called the load average. And this is, I think, 5, 15, and like an hour long running average of these numbers. What you want to do is you want to look at these numbers. If these numbers are really high, and high is relative to how many processors are in the computer, but typically if these numbers were like 15 or 20, I would go to another server. I wouldn't even bother launching Cadence because it's usually going to be very bad. These numbers, 0.42, 0.14, nobody is using this. And you can see this here. Nobody else is on this server. It's me, and it's just me. So it's only my account. All right, another great command is that many of you have asked if, Miriam is going to email you back or not. What she essentially is doing is adding you to a group, and this group is what's giving you access. So if you want to check to see if you're added, you can type the command groups. And so in groups, what you're looking for is this last one, this ING6 IBM PDK. If you do not see this, that means that you do not have access to Cadence. So nothing that you can do will fix that other than following up with Miriam to get access to it. All right, so we have that. If we wanted to start Cadence, we would run Virtuoso. All right, there's a couple of windows in Virtuoso that are really important. This window here is what's called CIW. This is where it sends a lot of the error messages and anything else that's happening. And so if we scroll up and we look at this, this is just that it's launching Virtuoso and it's loading all of these files. Our setup file is not quite right. Somebody messed it up, and so there's this error. It's okay. It's not a big deal. And then it has a few other warnings from that it's missing triggers. And so if we open up the library manager, this is where we're going to organize all of our designs. And so, I have a folder here that's called EE164, and I've created a schematic called test. This was just something that I did yesterday to make sure that it was all working. And so I've drawn here a fairly simple schematic. It's just an inverter. A voltage source. This is what I'm using as my supply voltage of 1.8 volts. And I've called this VDD bang. VDD bang, anytime you see a bang on any of these, it means that it's a global net. It's something that it's going to use anywhere on all of the schematics. We probably will not have many designs that have too deep of hierarchy, but if you wanted to share it, this is the equivalent of like shared variables in programming. They're global across all the functions that are in that file. And then I have a voltage source here that's going to generate my input voltage Vn. I've connected a PMOS and an NMOS device. And then most importantly, and probably one of the most common mistakes that people make, is you have to reference this to ground. So everything in circuits, voltage, it's a differential measurement. And so we need to tell the simulator what we want to reference this against. And so what I put in here is this ground symbol from the analog lib. This tells the simulator, this is what I want to be 0. So all of these other voltages are relative to 0. The other thing that will happen when you put in a transistor, in particular in this technology, it's going to add this net for you. Okay, it's going to drop in this net called sub. And if we zoom in a little bit, it says this is from TN0. And TN0 happens to be this MOSFET. Okay, this is really the substrate. And so what I want to do is I want to tie the substrate to ground. Now, the interesting thing is that if I try to just directly connect these two, it's going to give me an error. Why do you think it's going to give me an error?
Shorted.
Yeah, so it doesn't like that this net right here is named ground, because that's what this symbol does. This tells it that it's named ground. And yet this net is named sub. And so it doesn't like to short two nets that have the same name. And so the easiest way to do that is to, in our analog lib, we can add a resistance, and we can make this resistance very small. We can make this 1 ohm. And now when I save this, now all of a sudden I don't have any errors. The other thing that you should always look for is warnings. So if you hit Shift G, it will show you warnings. It will also highlight warnings on the schematic. So let me give you an example here. Right now, when I save this, there's 2 warnings, okay? And these warnings are happening over here. This warning in particular, if I hit Shift G, it says floating net, V out. So what this is saying is that it doesn't like that I just have this wire dangling out here without anything connected to it. And so what I've done is I've put this other little symbol. This symbol is called nocon from the basic library that says, don't worry about it, ignore that error. And so now when I save this, I won't get any warnings from this. All right, and then this is what we're going to call the schematic window. ADE, so this is the analog design environment. That's this window here. This is where we can set up things like what type of simulation we want to run, what we want to measure. And so I've set up a DC sweep, which I'll rerun it here. And so what I've done is I gave this voltage a parameter so that I can sweep it, Vn, and then I set up a DC simulation where I'm sweeping Vn from 0 to 1.8. And so now when I run my simulation, this is what pops up. And so what happens here is this is telling you that first it's reading in all of the files, then it's going to actually tell me any warnings. And so I want to look very carefully at these warnings. Then it's going to go through and it's going to do its simulation. So here it's showing you that it's 4%, 8%, 10%. Now it's 100% done. And then at the end, there's no errors. And so if I now plot some of these, I can plot the output and I can plot the input. And I end up with a curve that looks something like this. And so the input, this is just showing V in versus V out. So that's a linear line. This is showing my MOSFET, my circuit, where it's switching, right? And so using this, I can figure out the exact switching threshold of this particular circuit. And if I wanted to move this back around, I could size this device much larger. So instead of 3 fingers, let's just say that I do 30 fingers. And now I save and rerun my simulation. and now I plot my output, you can see that we've moved the switching threshold. And so by making that PMOS device stronger, I scooted this device over to the right. I could do the same. I could make the NMOS stronger and I could scoot it back to the left. That's all about how we size an inverter for its switching threshold. But if you are having problems running the simulation, one of the very first things to look at is to look at the output log. So this file, it will tell you if there's errors with your circuit. It will tell you if there's warnings that you should look at. This particular warning, it's okay to ignore. Any other warnings, I would look at very carefully and make sure that you understand what it's trying to tell you. All right, are there any questions about getting Cadence, using Cadence? Anything else that I can help on right here? Okay. All right, well, if there's no other questions, then I'm going to go ahead and end today's discussion section. Next week during discussion section, I'll probably do a couple of examples and again, answer any questions that you guys may have. Thank you. Have a great week. Bye.
And just out of curiosity, why does this software cost so much? I mean, why aren't there any competitors and why is it costly?
Yeah, there are a couple of competitors, but there's been a lot of market consolidation. And so there's really, Cadence is truly the industry standard tool. There are other tools from companies like Mentor Graphics that are somewhat competitive, but they're not nearly as popular as these tools. And so when you have consolidation of these tool vendors, you're just left with limited choices.
Okay, so it's a monopoly.
Yeah, exactly. I mean, there's nothing great about this software. And in fact, a lot of ways it's not great, but
exactly.
You should get used to it. Oh, I should mention just 1 second about plots. So, in general, Cadence is really bad at making good plots that you can submit for your homework. There's a couple of ways to do better plots. You can use export image. And here, one of the worst things about the Cadence plot is that it has a black background. And so you can swap the background and the foreground and you can make it white and change this to like black. This usually results in much, much better figures that you can either save to file or copy to your clipboard. In general, though, taking screenshots of just this and trying to turn them in, they can work, but it really is up to you to make them readable. If I zoomed out like this and I submit a homework that looks like this, it's really hard to see what's going on. So, think about the TAs and think about how you can try to get the best plots that you have given the software is what it is. I'll show you some more examples probably next week of what looks good and what doesn't look good. All right, any other questions about Cadence?
Yeah, I have a question.
Yep.
Yeah, I saw in the tutorial, each time we open and analyze, we need to tap the TT in the model library setup.
Yeah.
Each time we need to do that.
Yeah, so in here, you have this model libraries, and when we click on all models, it gives you a lot of choices. We will talk about what these are. You don't know right now, but TT is for typical. And so typical. That's the one that we should always select to start with. Some of these other things like fast, slow, fast, slow, we will talk about them, but you don't need to do it. Importantly though, and I'm glad you brought this up, it doesn't default to anything. And so if you forget this, and now we try to run this simulation, we're going to see down here that it says Spectre terminated due to a fatal error. And if I scroll up for a little bit and I try to figure out what's going on, it's going to tell me all models, illegal library definition found in netlist. It doesn't quite know what it means, but what it's trying to say is that we haven't given it any model files. We didn't pick one of them. So to fix that, what you do is you come in here to the model libraries and you tell it that we want to simulate with TT. One other common thing that that happens a lot is that this right here, depending on what server you're on, it used to be the case, it's no longer the case, that we had both 32-bit and 64-bit servers. If you get another error, you need to come in here and check this to always run with the 64-bit binary. Other questions?
Wait, where did you go for the environment options?
Yeah. So setup, environment.
Oh, okay, thank you.
All right. Any other questions? All right. Well, good luck with homework 1. Please start early. Don't save it until the very last minute. And please, please, please do not use your freebie on homework 1. Homework 1 is the easiest of all of the homeworks. Save your freebie for one of the more difficult homeworks or if something else does come up. All right. Bye. Have a good week.